Thank you for joining us today. Our next talk is entitled Breakthrough Yield Barriers with Siemens and PDF Solutions. So this is a joint work that was done between us and Siemens on the testnet organization and PDF Solutions. To discuss this work, we'll have Thomas Zanen. Thomas is the engagement director at PDF Solutions. He has about 17 years of experience in the semiconductor industry and is a technical lead for the Siemens and PDF integration collaboration work. Thomas held multiple roles at PDF Solutions in development of the bitmap solution, design for inspection, DFI, and yield ramp consulting projects. Thomas holds a diploma of engineering in electrical engineering and information technology from the Technical University in Munich and a PhD in EE from Carnegie Mellon University in Pittsburgh. Please welcome Thomas.
Is it muted? Okay. Hi, everyone. All right. So today I want to present the collaboration between PDF and Siemens and the projects we have that come out of that collaboration. So first, a quick motivation of why this collaboration happened. So one very continuous trend in the semiconductor industry is clearly the migration to new technology nodes. And of course, with every new technology node, typically the manufacturing complexity increased. And at the same time, the products that come out of those new technologies, because of the added capabilities of those new technology nodes, also get significantly more complex. So clearly the pressure on the failure analysis and on fast yield learning increases dramatically. And in order to reduce the rising cost of the manufacturing and meeting the demands, the market demands for new products, it's necessary to have efficient solutions. That's what we call the integrated solutions that take the data from multiple domains. Essentially, we want to combine design, manufacturing, and testing in order to facilitate a faster yield learning. So the way PDF Solutions and Siemens tackle this is by leveraging the strengths of both the testnet environment, the testnet platform, with the strengths in PDF's manufacturing analytics platform. So we started building applications around those two platforms. The first application is an integration of testnet Yield Insight with Exensio manufacturing analytics. And that's mainly to combine the scan diagnosis that misses other product data with the product data that the manufacturing and yield data that are available in Exensio. In the second project, we're extending what's usually done in testnet Yield Insight on random diffectivity to include layout pattern systematics. So essentially, we try to tackle layout sensitivities in products. And for that, we're using the layout analysis engine that PDF has available. The third project goes now out of the logic part of the product. It goes into memory. So clearly, products get more and more complex in terms of embedded memories. So we found a good fit in combining the testnet environment, Silicon Insight, as well as memory-based, of course, with the bitmapping solution that Exensio has. So first, in the first project, which is the combination of volume scan diagnosis with yield manufacturing data. So you know probably about Siemens diagnosis-driven yield analysis, DDYA. This is a very proven methodology by now to extract valuable failure information from the scan test data. It's using as main components the layout-aware scan diagnosis, layout-aware diagnosis in testnet diagnosis, as well as the statistical analysis in the root cause deconvolution in testnet Yield Insight. So both combined, they do provide valuable information about the root causes by generating defect paretos. And in addition, they also enable PFA's candidate selection by providing localized failure information. But the effectiveness of this DYA flow and also the quality of the results you get out of this flow, it's strongly depending on the quality of the selection of the filling dies that go into the analysis. And here is where we jump in with from the PDF side, since that flow is working off the scan diagnosis data, or the scan test data only. So now we bring in the other available product data that are in Exensio in order to get the more comprehensive analysis and ultimately a better selection of those failing dies for the work in TYI. So essentially we need an efficient solution that uses all the product data to identify the best die population, and that's the combination, the integration with Descent, Yield Insight, and Manufacturing Analytics Exensio. So I will show first a slide of overview slide of that integration work, and then I will show 2 slides of sample flow, typical sample flow of that now enhanced analysis. So we have on the right side, we have Descent Yield Insight that uses the Descent diagnosis reports. On the left side, we have Exensio that handles a lot of the other data that's available coming out of either inline or testing. So we have essentially all those yield and manufacturing data, and they are stored in a database. So the first step of that integration is bringing in the information that's in the Descent diagnosis reports into that Exensio environment. So we're reading those metadata in. Now the tools are now aware of what's happening on both sides. And that essentially enables now additional functionality that can be used for more comprehensive analysis. For example, what we can do now is we can use very large data sets and analyze them in Exensio, and with the goal to filter out an optimized die population instead of going straight into Descent Yield Insight. We have worked on all the efficiency to move this set between the tools, this information very quickly. Now, in Descent Yield Insight, you can do your typical analysis. It's fully it has all the capabilities that you are used to use. You get your suspected root causes, you do a selection of PFA candidates, but now instead of going there straight to the PFA lab to do submission for the PFA lab, you can go back again to Exensio and do a very specific detailed on this set analysis of which final PFA candidate you want to send to the PFA lab. So this works now as follows. This is an example data set of 200 wafers of scan diagnosis data. And if running them unfiltered will probably generate quite a few root causes of interest. In the integration, the idea is now you use those 200 wafers in Exensio. You use the non-scan related data do the filtering. For example, one obvious filtering is typically looking for similar wafers, doing spatial signature analysis. In this case, for example, on the sort bin data, that already makes those wafers, the dies on those wafers more similar. Then you can bring in any other data types and do more refinements. You can use what data. If there's inline data available, you can use that one as well. Essentially, the goal of this refinement step is to get a die population, essentially a die set that has a much higher commonality than if you do than the unfiltered original die set. Data is then transferred, and then you run your analysis in Descent Yield Insight. And for example, in this case, you would get the RCD defect Pareto with only one root cause, or at least fewer root causes. So this will make the analysis in Descent Yield Insight more precise. And now, since with all this pre-work, now it's also more likely to get PFA candidates with a better success rate. Those PFA candidates or RCD suspects connected to these PFA candidates, you select them the usual way in Descent Yield Insight. And so I'm talking here about the step going back to Exensio. So once you have those PFA candidates selected, you can be more liberal in how many you select, because now you can go back to Exensio. Actually, you also put snippets there, so you can look at the layout snippets in a gallery in Exensio as well, so you learn more about where those fails happen. now in Exensio, you can do a drill down on those very specific suspects to figure out which one you want to use for PFA. For example, one idea is you maybe want to have the suspects on dice in a specific IDDQ range, right? Or in this example, I know most folks don't have inline defect data, but you could potentially bring inline defect data, which completely makes your PFA unnecessary if you have an overlay hit already, right? So the idea here is that we combine now essentially the manufacturing side, the yield side with the design side that's in the layout aware diagnosis. And by combining all those domains, the goal is to get a better PFA success rate, which is, of course, always a critical item to achieve. So based on that, so this, as I mentioned before, was random defectivity mostly, right, in RCD. So what we try in the second project and the second application that tries to tackle now systematic behavior in the products. And so as mentioned before, DDYA volume scan diagnosis with RCD is a proven methodology, but it's very focused on random defectivity sources. And it's very clear that there is quite a few patterns in a design that show systematic behavior. And that obviously yields to systematic yield losses. There's attempt to try to resolve those issues very early in the technology ramp, and every time a new product is introduced, also early in that product's ramp. But it's been observed that at least in recent technologies, some of those systematics, they're actually very sticky. They stay all the way into volume manufacturing. Essentially, they prevent you to get the true entitlement yield. So it makes sense to address them and include them in the analysis. So what we do in this integration is we're working on making RCD defect Paretos more accurate by including layout pattern systematics in addition to random defectivity sources. And we do this by combining the RCD decintilled insight with PDF's FHIR layout analysis engine that's used for extracting layout pattern systematics. So the flow for this works as follows. So we use FHIR to extract layout patterns, layout pattern systematics. This can be either based on hotspots, non-hotspots, or you do detailed analysis of net repeater fails. Once you have those systematics, it could be many. FHIR has an automatic grouping feature that combines them into what we call pattern families. And those pattern families are then imported directly into the Descent layout database. So this is typically a process that happens once for a product, but of course, if new inputs come in, then it can be run again. But it's not something that needs to be run for every volume diagnosis run. Once this information is in the layout database, the usual collection happens of the scan test fail data, then volume diagnosis is run, and the Descent diagnosis reports are generated. The only difference now is they will automatically now, and those diagnosis reports will be automatically annotated with the pattern family information that's in the layout database. So essentially, the diagnosis reports now do get the systematic layout pattern systematic information included. And then feeding this to RCD, the root cause Paretos that will be spit out by RCD will now include both the random defectivities in addition to now the layout pattern systematics. So we ran benchmarks on this flow by generating first we extracted, of course, layout pattern systematics for the design and imported it into the Descent layout database. Then we generated a dye population that has 3 different root causes. So this was a relatively simple benchmark at this point to try it out. And in the top table shows those sources. So we included random M2 shorts with a certain percentage, cell internal shorts. So I'm mixing here RCD, ARCAT. So we ran ARCAT, but the fails, the systematics are mostly in the backend so far. And then we introduced also layout pattern systematic M2 shorts. We ran the default ARCAT, so the one that does not include the layout pattern systematics. And for that reason, obviously, no layout pattern systematics are identified. And if you notice the random M2 shorts, the attribution coming out of the ARCAT is now much higher. So the problem was here, and that's the inaccuracy by not handling the layout pattern systematic specifically. Now, random defects the system thinks layout pattern systematics are random defects, and that's how there is a mismatch. Then we ran the same set of diagnosis reports through the now updated ARCAT that includes the 5 identified pattern families. And now we see that it successfully identifies those layout pattern systematics, and it also separates many of them from the random M2 shorts, because now the random M2 shorts, the injection rate versus what ARCAT attributes is very close, right? So the idea behind this one here is, it was very obvious was how much the value is to separate random from layout pattern systematics to overall increase your defect Pareto accuracy. We ran also much larger benchmarks, multiple sets of at least, and large dye populations that have at least 10 injected root causes. And what we learned from those benchmarks is that typically we have around 90% accuracy in identifying those layout pattern systematics. And in addition, more than 90% accuracy in attributing a dye to the correct injected root cause. So now I'm leaving the logic side of the products and go to the third project on the embedded memories. So the complexity that's seen overall in the product with the new technology nodes is also clearly visible in the number and the complexity of using embedded memories in those products. So, but now lots of the most complex products already have more than 10,000 individual memory instances, hundreds of MBIS controllers. So it makes the failure root cause analysis of those chips, why those memories fail, very difficult. But even before you even start analyzing, handling the setup for memories, for products with so many embedded memories, for doing analysis is actually very time consuming. It's not trivial. You definitely need a good, efficient solution for handling those kind of products. The way I mean Siemens and PDF envision to make this efficient solution is by combining Descent's memory environment. So here meaning memory-based technology and the Descent Silicon Insight application with Exensio Manufacturing Analytics. Descent memory-based is proven technology. It's used widely to collect fail information from those complex embedded memory products. Descent Silicon Insight can be used to debug and characterize those memories, but what you don't have in this solution is any kind of volume analysis that you can do. This is where we have non-overlap with what we have on the Exensio side. On Exensio, we have a bitmap solution that does all the analysis efficiently for those memory test data, and it also provides the analytics and diagnostic tools to do the analysis, and in the context also with other product data, of course, because we have the whole Exensio Manufacturing Analytics environment. But what we don't have, what always was very difficult every time we set up bitmap, is we don't have a standardized input of how those memories are defined, and that's where it's very useful since everything is standardized in the memory-based. So combining the two solutions, the two platforms, now we can offer a single memory analysis platform going all the way from inserting the BIST, reading out the BIST, and reading out the fails of the memories and doing the analysis. So I will now show an overview of how this platform, this single platform works. So we use the first step is a setup. So we use the memory configuration that's part of the Descent Silicon Insight environment. And it's already there because the memory-based infrastructure got inserted into your product. We use all this information to automatically set up the descrambling, which is always a necessary step in any kind of memory analysis. And we also set up automatically everything that's needed for doing bitmap classification. So this is a very efficient way for a new product to be set up. During the memory testing, you will get ultimately logical bitmaps, electrical logical bitmaps out of this testing. Then we use the previously generated setups to do first the descrambling to get to topological bitmaps, and then we classify the bitmaps. And at that point, you have now the bit fail signature that are needed for doing volume analysis of memory fails. We load them into the Exensio environment, and there in our PDF's bitmap module, you have all the tools to do the analysis. And since the Exensio bitmap module is just part of the bigger framework in Exensio Manufacturing Analytics, you can also now easily combine the analysis, the memory analysis, with all the other product analysis. Potentially, you can bring back in the scan diagnosis information from the first topic, right? And the goal here is, again, the goal is to get good PFA candidates, because that's ultimately, if you have a new problem you don't understand, you ultimately have to go down to BFA, right? So you have this comprehensive analysis framework now to get those candidates out. So I will now, summary slide is essentially just a summary of the benefits we see in combining the Descent Exensio solutions into an integrated solution. So we have on the Descent Yield Insight integration with Exensio Manufacturing Analytics, the key thing is you get an optimized die population for TYI using large data set analysis, yield analysis, and Exensio Manufacturing Analytics. And the goal is to get better PFA success rates. That's our driving goal. On the Descent root cause deconvolution integration with FIRE, we try mainly to address deconvolution of random defectivity from layered pattern systematics, with the goal to have more accurate RCD Paretos to handle systematic yield losses. And for Descent Silicon Insight memory-based integration with Exensio Manufacturing Analytics, we strive for an efficient setup of new complex embedded memory products and ultimately get a comprehensive memory fail analysis. Thank you.